Good morning. I wanted to help you differential equations, students with Chapter 7, Laplace Transforms. The birds are chirping out here. Maybe they won't be too loud. Laplace Transform, we denote it like this. We take with capital L, we take the Laplace Transform of a function, f of t. And what that means is this. We do this integral from 0 to infinity, e to the negative st times that function f of t dt. So that's the definition of a Laplace transform. That's the definition. Notice something here. The variable of integration is t, but there's this other variable s, but we treat it as a constant. The variable of integration is t. So you do this integral from 0 to infinity, and there'll be this sort of constant s that you chase around. So in the end, the answer is going to be some function of s. So we denoted capital F of s is the answer. So we should try an example. So let's try the Laplace transform of e to the 2t. So in order to do this, I'm going to do an integral from 0 to infinity, the definition, e to the negative st times the function here, e to the 2t, dt. So now my job is to do this integral. You know, this is an improper integral, and technically the way you do it is you take the limit as b goes to infinity, and you go from 0 to b. And then I'm going to try to integrate this. Now let me gather it together here. You know what I want to do? Let's see, if you're multiplying bases, you can add exponents. And then if I factor out a negative t, I'm left with a positive s minus 2. I hope that wasn't too many steps for you there. But what did I do? I added those together, e to the negative st plus 2t. And then I factored out a negative t, leaving me a positive s minus 2. Yeah, that's good. So I went from here to here. All right, I'm integrating with respect to t. So hopefully you know how to integrate an e function. It's just himself, but technically you do a little u substitution, and it's going to spit out a negative 1 over s minus 2, a negative 1 over s minus 2. We use these s's in Chapter 7, Laplace Transform. Watch out, sometimes they look like 5s, okay? They're s's. Anyway, here we are. We're going to evaluate this from 0 to b, and then, of course, take the limit as b goes to infinity. If I plug in the b for the variable t, I get negative 1 over s minus 2, e to the negative b s minus 2, minus negative 1 over s minus 2, e to the, what am I doing now? Oh, plugging in a 0, e to the 0. All right, there's my answer. I plugged in the b, I plugged in the 0 for t, and then I need to take the limit as b goes to infinity. Of course, e to the 0 is a 1, so of course this is a positive 1 over s minus 2 here. But what happens here? As b goes to infinity, what I want to happen is I want this to go to 0. As b goes to infinity, I do get e to the negative infinity. That will go to 0. But technically, it's only a negative infinity as long as this is positive. If this was negative, it would make it a positive infinity, and I don't want that. I want it to be a negative infinity, because then it'll go to 0. That means I want that to be positive, which means I want s greater than 2. So this does go to 0, and it's 0 plus this, and the answer is this. But there was just a little technicality that s has to be greater than 2 for that to happen. So a little comment here. S is greater than 2, makes this go to negative infinity, makes that go to 0, and there's the answer. And the Laplace transform of e to the 2t is this function f of s, here it is, 1 over s minus 2. So that's using the definition. I don't have too many homework problems that make you use the definition. What happens after we could practice a couple more, but after we use the definition, I'm going to get rid of this, we end up using memorizing a bunch of Laplace transforms. But we don't actually memorize them. Here's some famous ones. They come in a table in the back of the book. Here's some famous ones for you, though. The Laplace transform of a 1. I think that's 1 over s. The Laplace transform of a t. That's a 1 over s squared. These are s's. The Laplace transform of just a t to any power n would be n factorial over s to the n plus 1. The Laplace transform of an e to the at. We just did e to the 2t. The answer is 1 over s minus a. The Laplace transform of a cosine k times t for any k is s over s squared plus k squared. The Laplace transform of a sine kt is different. It's a k over s squared plus k squared. So these are famous Laplace transforms, and we should memorize them. But that's actually not true. They're actually in a table in the back of our book. We have a table of Laplace transforms, the very back hardcover of the book, table of Laplace transforms. I mean, maybe you should, I don't know, anyway, you should have this readily available when you do your homework, unless somebody says do it using the definition, in which case you sort of have to derive these formulas using the definition. So we use these, and once we use these, we can, let's try a couple of examples here. Getting rid of the definition, let's try a couple of examples. What if I want the Laplace of a 3t squared? Well, you know, here's one rule I forgot to tell you. You're allowed to pull out a constant. Actually, let me say something. They call this the property of linearity. Property of linearity. Derivatives have this property. Integrals have this property. You know, derivatives and integrals are transforms, actually. I mean, actually, this Laplace transform, I just erased the definition. This Laplace transform is an integral. A special type of integral, but it's an integral. And regular old integrals and regular old derivatives are also considered transforms. And they have the property of linearity, which I'm going to express like this. If I want the Laplace transform of some alpha times f of t plus or minus some beta times g of t, then the answer is alpha times big F of s plus beta, where alpha and beta are just constants, times big G of s. In other words, what did I just say? That if you're doing the Laplace transform of separate functions added or subtracted together, you're allowed to distribute the Laplace transform and do separate integrals. We know that with integrals. We know that with derivatives. Also, if you have a multiplied constant in front of your function, you're allowed to pull it out front and do the Laplace of that function. So you pull the alpha out front and do the Laplace of the function. You pull the beta out front and do the Laplace of that function. We do that with derivatives and integrals. So that's an important property that allows us to do a lot of Laplace transforms. Let's try this one. So in other words, I can pull the 3 out, and then basically I'm doing the Laplace transform of t squared. If I refer to this, what is t squared? That would be a 2 factorial over s cubed, 2 plus 1, 2 plus 1. There it is. 2 factorial is a 2 times, yeah, so you should clean these up a little bit, but there it is. Let's try another one. Let's try another one. I'm going to get rid of this. I'm going to get rid of some of this here. Let's try the Laplace transform of 4e to the negative 2t minus 3 cosine 6t plus 2 sine 6t. All right, here we go. Guess what? You're allowed to do 3 separate Laplace transforms. Remember, that's what this says. The Laplace transform of him, the Laplace transform of him. So here we go. Oh, and you're allowed to pull out the constants. So basically, I'm pulling out the 4, and I'm doing the Laplace transform of e to the negative 2t. According to the rule, that I just erased, it's 1 over s minus a. 1 over s minus the a, which is a negative 2 in this case. So that'll be s plus 2. A 3 cosine 6t. How do we do cosine 6t? Here we go. It's a 3, and then the rule is s, that's an s, over s squared plus the k squared. The k is the 6, s squared plus 36. What about 2 sine 6t? Well, that's going to be a positive 2, and then the sine has the k on top. So the k is a 6 over s squared plus 36. So there's the answer. We did the Laplace transform of that using these famous Laplace transforms. Like I said, I like to memorize them, but the truth is you get to have that Laplace table in the back of your book. So you get to have that to reference that. But some of these real famous ones, I mean, these are very common. It's better, I mean, it's nice to have them kind of memorized. I'm just going to clean that one up a little. That's a 4 over s plus 2 minus 3s over s squared plus 36 plus a 12 over s squared plus 36. You know, you may see this written then like this, s plus 12, 3s plus 12, because they have a common denominator. This minus sign is in, wait a minute. The minus sign was on him, okay. Negative 3s plus 12, s squared plus 36. What happens next, so that's 7.1. You should practice some 7.1. What happens next is we do Laplace inverses. So we read the table backwards. We try to do the Laplace inverse of this to get back to this. So we learn how to do Laplaces forwards, and then we learn how to do Laplace inverses backwards in 7.2. That'll probably be the next video. There's nothing more to say really about it. This is 7.1. All right, good luck.